The mission for the Reaction Plan Manager ++ software is to give the operator on the shop floor the information needed to keep the manufacturing process running smoothly. RPM++ offers a rich set of tools to allow the engineer to calculate the process correction amounts used in the operator instructions. In this video, I will introduce a tool called links. Links are very powerful. They're used to share data between dimension items. I'm going to describe a few applications which are common in manufacturing and show you how links can be applied. Assume a manufacturing process uses two tools to produce a part. Tool 2 machines features that are relative to Tool 1. So if the operator has to adjust machine parameters for Tool 1, he must also adjust machine parameters for Tool 2. The Tool 2 adjustment amount must capture the Tool 1 shift plus the corrections needed for the two tool features. A process shift link can be applied to this type of situation. In one report, you can capture this condition and calculate the adjustments required for both Tools 1 and Tool 2. I'm going to now demonstrate that application. Here you can see I've got Reaction Plan Manager ++ running. Down here in the lower right hand corner of my screen, I've got a simulation software running that'll let me simulate measuring a part on some sort of measurement machine. Now those of you that use QC Calc real time, the data would flow through QC Calc real time and QC Calc would send the data to Reaction Plan Manager ++. But in this demo, I am not going to use that. I'm just going to use this data simulator here. So if I click on the inspect button, it will run the part program link-process shift. So I'm going to go ahead and click that button to inspect the part. In the detail view of the solution, I can see a picture of the part, and there are notes here which are telling me that Tool 1 machines the surfaces and Tool 2 machines the grooves. Now you can see I've got three surfaces here that we've got marked, and we've got two grooves that are marked. Notice that this groove is tied back to this surface. So if I adjust the distance, this distance here, which is controlling this surface, it will affect the location of the groove. So Tool 2 is tied to Tool 1. If I make an adjustment to Tool 1, or in other words, this dimension, it will directly affect this dimension. In this example, the Tool 1 pulley snout height is linked to the Tool 2 snap ring height. When an adjustment is required for the Tool 1 pulley snout height, it'll automatically pump a process shift to the Tool 2 snap ring height. It's done automatically. Let's go ahead and inspect some parts so we can simulate what happens when a reaction occurs, an action occurs. So I'm going to keep clicking inspect until I actually get something go out of tolerance or require some sort of adjustment. Now, this is designed so it'll start shifting out of spec. So we're just about ready to get out of spec here. Alright, so we've got a condition where an adjustment is required for the Tool 1 pulley snout height. It's telling us we need to adjust the tool by -0.00475, which is the correction amount from here to here. Notice our Tool 2 snap ring height also is requiring an adjustment. It automatically triggered when this adjustment was requested. You'll notice the kind of a grayed out or half visible icon here, this represents your process shift. This is where the actual dimension is, but we incurred a process shift from the link. And so this is where the process shift really ended up being. So now it's telling us to correct by this amount plus this amount to get us back to our target position. If I expand this and look at it a little closer, you can see a process shift of 0.00475 was added to this dimensional item, which came from this deviation here. In one analysis, we have all the information needed for the operator to properly adjust tool 1 and tool 2. You probably notice that the link didn't happen until a rule violation occurred for the tool 1 pulley snout height. And then when the link occurred, there was one action, and the action was to share the deviation from nominal to the tool 2 snap ring height. When you configure a link, you will tell it when the link occurs and what actions to take. So if I had multiple tools that were affected by the tool 1 pulley snout height adjustment, I could share that data with all the different dimensional items that control the other tools. The important thing to take away from this is that you can configure your analysis so it gives you all the adjustments that you need in one report. I just demonstrated how to apply a link to a process shift. Can links be used for other things besides process shifts? And the answer to that question is yes. Let's run another application and see what happens. I'm going to run the link-simple hole diameter simulation. In this example, we have a manufacturing process that's producing 6 holes. And we're displaying the diameter of each individual hole. Now the way this is set up, if one of the holes requires an adjustment, you're going to get the appropriate instruction. The reality is it's probably the same tool that's producing all 6 holes. So if we're interested in the size of the diameter, a better way to evaluate that would be to look at all the holes, like an average of all the holes. In other words, you want to look at all the holes as a group. Well, using links, you can design a solution that will evaluate the 6 holes together. I'm going to run another simulation that does that type of analysis. I'm going to run link-hole diameter summary simulation. So I'll click on the inspect button and it will run that particular reaction plan, or that particular solution. To understand this analysis, we need to talk a little bit about how data is received in a dimensional item. The default data source for a dimensional item comes from measuring a part. So each one of the dots would represent a unique part. You can change the configuration of dimensional items so the data source is a link. When the data source is a link, the only time data will enter into the dimensional item is if it's pumped by a link. In this example, we have the 6 diameters over here. Each one of these dimensional items represents the diameter of measuring a part, and they're linked to this dimensional item. So each one of these dots represents a different diameter. Now you'll notice we have the last run info set so that the number of items is set to 6. So the average of these 6 parts represents the average diameter, that would be what we'd be interested in with regards to making an adjustment to this process. this dimensional item is linked to this one. So the ultimate average, or the average of the last 6 holes for the last part, would be here. Notice we only have one part here. Each time we measure a part, you'll see 6 new diameters here and 1 part here. So let's go ahead and measure another part. And you'll see the data change. And now we have 2 parts. This is the data for the last part, for the last 6 holes. This is the data for the last part, holes 1 through 6. And here's the average of those last 6 diameters. To interpret the results of this analysis, I would use this information to tell me if my last part was good. All these diameters should be in spec. And I can use this dimensional item to tell me how to adjust. So if I need to make an adjustment, I can use this information to figure out how much to adjust by. We really don't need to display the individual diameters here because we have that information here. So if we mark these dimensional items as auxiliary, the link will still occur, but we just won't display that information. So let's go ahead and quickly change that. I'll use the quick dimension edit to quickly mark those diameters as an auxiliary with an auxiliary type. So what that means now is we only have the 2 dimensional items because that's really all we need. So if we do more inspections, we can see the data flow into the solution. Let's go ahead and shift the data. Okay, you get the idea. If this is a real application, you'd probably be interested in the hole locations as well as the size. Let's go ahead and run another simulation to show that information. Looking at the analysis, you can see we have 2 holes, holes 1 and 6, has some instruction information. This report is rather busy. You have a lot of dimensional items scattered out throughout the report. This is only 6 holes. Can you imagine what it would be like if it was 20 holes? Well, let's look at another analysis and see if we can come up with a better way of displaying this information. This analysis is similar to the diameter analysis I showed you earlier. Instead of dealing with the whole diameters, we're now dealing with the position and location. This column of dimensional items, these 3 dimensional items here, represent whole data. This column of dimensional items, these 3 here, represent part data. So data is pumped into these dimensional items from the whole locations, and then data is pumped from these 3 dimensional items to these 3 dimensional items. They're all linked together. Let's talk a little bit about each set of dimensional items. So you can actually see it better. I'm going to uncheck the shrink to fit so we can zoom in and see the dimensional items. If we look at the first set, the location, or the last part, true position of holes 1 through 6, you notice we have 6 points here which represent the true position of each one of the hole locations. And over here, we've got a link to the maximum true position error of holes 1 through 6. So instead of looking at the average, we're grabbing the maximum deviation for each one of these holes, and we're keeping that. So the maximum deviation for this set of data is 0.00398. So that's what's pumped over to the maximum true position error of this particular dimensional item. So we've got 0.00398 here. The next set of dimensional items tracks the X error, the X deviation error for each of the holes. So each one of these dots represents the deviation, the X deviation. So we're pumping the average X deviation over to this dimensional item. And the bottom set is tracking the Y deviation. That's what we would be interested in if we were making the adjustments. We would be more interested in the X and the Y deviations. The average of those would represent the pattern error. So you could apply some adjustments using that information. So I'm going to go back and shrink to fit so we can see all the dimensional items. Now at a glance, I can tell that the part, the 6 hole locations on the part are good. The error seems to be small. The locations are fairly centrally located. So let's go ahead and inspect some more parts and see what happens. Now I've got this simulation designed so that it's going to shift the data. And when it shifts the data, it's going to cause it to shift in X and Y, and it's also going to cause a rotation as well. So let's see what the data looks like as we inspect some parts. Now notice the variation in the data for the Y and the X starting to kind of transition back and forth to more of a curve instead of a line. That indicates that you have some rotational error in the pattern, and the true position is showing you the same thing. So we've got some rotational error, but we're still in spec. If we keep running this, we'll notice that eventually it'll go out. All right, so the true position, the maximum true position has we've got a percent of tolerance violation up here, and it's telling you the whole pattern needs attention. So since you've got rotational error, you really need another tool like the bolt pattern analysis software to really figure out what's going on with the pattern and calculate the adjustments. But at least this gives you an idea as to what's going on, and I do need attention to the whole pattern. Also note that I could have 10, 20, 30 holes in here and control all 30 holes by looking at this data. And at a glance, I could tell you if those 30 holes are in spec or out of spec, and get an idea of what's going on with the process. In this video, I introduced a link feature available in the Reaction Plan Manager++ software solution. I showed you several examples. The first example used links to apply a process shift. The other examples use links to provide better information about a process. Links are extremely powerful and can be used in a variety of applications. To learn more about this topic, visit www.beckerqualitysolutions.com and click on the RPM++ help video link.